In the first lab, we will learn how the microcontroller manages its peripherals. So we will make a simple program that turns on or off some LEDs, but we will do it in a special way so that we understand how it's done inside the processor. So let's first make a new project. If you have to attach the development kit to your computer, and if you have done it correctly using mini USB cable, then if you click on the board and click on documentation, then automatically you see some data sheets about this particular chip that is on your board. In your case, it says Giant Gecko starter kit. In my case, it's Leopard, but they're almost identical. So mine is a little bit older. So you have a bit newer development kit. So it says Giant Gecko here. So if you click on this Giant Gecko starter kit and click on documentation, you see that here um, you have, for example, user's guide, and it also contains Leopard Gecko starter kit's user guide. For example, I can click on it and it automatically opens me the proper starter kit user's guide. And here you can see your development kit. Older version has a little bit different headers, but generally they're almost the same. So to properly connect your development kit to your computer, you need to use this Debug USB connector. It's mini USB connector in which you plug the development kit and connect it to computer. Do not use this micro USB connector. It is EFM32 USB connector, which connects to this chip. We will use it later at the end of this semester in the laboratory work about USB connectivity. But initially the USB is disabled. So this EFM32 USB connector you do not use. You only connect to this debug USB connector. Connect the cable here and to your computer, and this development kit should automatically show up in this debug adapters part of Simplicity Studio screen. Okay, so what we want to do is we want to make a new project where we write some code and we flash it into the development kit and everything just starts to work. So we click on new project, and then you can use an example project or you can make an empty project. We will try to use an empty project. So to do that, I click File, New, Project, and in this wizard, I have to select Silicon Labs MCU project. I click Next. The board part and SDK is selected automatically. It should show you the proper part number, development kit name, and this should be Gecko SDK suite. Let's click Next, and you have an option here to select empty C, C++ example library. So C++ is not very popular among microcontrollers because it usually uses a lot more space in microcontrollers. So even today, decades after invention of C programming language, everybody still uses C programming language for microcontrollers. So I select empty C program, click Next, and then let's give our project a name. And so the name will be, for example, project 2021 English for English kids, and click Next. Oh yes, and you leave link SDK and copy project sources in this option so that if you use some Silicon Labs libraries, they will be automatically updated during the update. So you would select this. If you wanted a standalone copy, you would select something different, but in this case, we leave it like this. Click next and don't change anything here and finish. And here we have our empty project. Even though we selected empty project, it's not completely empty because for these chips, Silicon Labs automatically generates some code. So let's check out the code. The first two lines include some libraries from Silicon Labs. Silicon Labs have written some libraries for us so that we can start to use their processors much faster. And unfortunately, when chips are produced, usually after some months of using the chips, it turns out that they have some silicon bugs. Rarely, only few processors in the world's history have been made completely perfect on the first try. So there is this chip init function, which tries to fix some bugs, if it's possible, for the chips. So Silicon Labs is not hiding it, they're pretty open about it. And in this Simplicity Studio, if you hold down the control key and click on a function with control click, then you automatically jump to the implementation of the function. So this thing is open, you can go into the function, you can try to check out what this function does and read out about it. So basically it writes some information in some registers, maybe fixes some calibration values and so on. And you can scroll through it, and some code is grayed out because it doesn't apply to our particular chip, but some code is not grayed out, it's active. So for example, this, if it's Silicon Labs 32-bit microcontroller from series 0, which is Giant Gecko series, and it's Giant family, then it writes some numbers in some registers to, as you can see, this fixes an issue with the low frequency external oscillator on high temperatures. So they have figured out that there's some mistake, but if some value is written to a calibration register, then the LFXO will start to work properly at high temperatures. So you do not delete this chip init function, you just leave it there as it is. And then after that, you can write some code, and there's also the infinite loop. So because you can go into Silicon Labs libraries and read their contents, and maybe if you feel smart, you can even edit them. This is why it's much better to use a microcontroller with all code available than, for example, Arduino. In Arduino programming, you cannot go into Arduino libraries and edit them. You don't have this control clicked feature. So this is why for very simple projects, you can totally use Arduino. It's not a sin, there's no problem about it. But in more complicated projects, people usually want to use embedded microcontroller with open libraries where you can go in and read everything and edit if you want to. Okay, so next thing that we need to do is we need to check out whether this project compiles. Even though I haven't written any code, we should try whether or not this code has no mistakes. So to compile a code, to try to compile it so that it's turned into executable code, you hit this hammer icon, build, and then this thing builds the code. And as you can see, under problems, there's no problems. And in console, you can scroll it up and you can check it out. If there were some mistakes, there would be red text. But since there's no mistakes, it's normal. And also at the end of compilation, I'll drag it a little bit bigger. At the end of compilation, it says build finished. And it also shows you the size of your program. So right now, the program is 872 bytes long. You might be wondering, wait a minute, this code doesn't do anything, just initializes the chip, but it already takes 872 bytes. It is because in C programming language, there's this thing called startup code, which initializes the chip, initializes stack pointer. It also sets all global variables to 0, all static variables to 0. It also copies RAM functions into RAM. So actually, before your main code is called, there is special things that the C program automatically does before going to your code. To check out what it is, if you want to, you can open this CMSys folder, open EFM32 Leopard Gecko, and there is this startup GCC code written in assembly. If you want to, you can go through it, check it out, and maybe try to understand what it does. There are some comments, but don't edit it. If you edit it and you make a mistake, then your processor will not work properly. And there's also this system EFM32. It is more about global variables like clock frequency and so on. But you don't edit them, but you can just read through them. Maybe you want to understand what they're doing. They're basically initializing the stack, initializing interrupt vectors, and initializing global variables, static variables, and copying things to random access memory if necessary. But that's it. Somewhere here, it calls your main function, and it basically jumps to main. But it takes some 872 bytes in flash memory. So the next thing that we want to do, let's make a conscious mistake in our code to see what it looks like when there's a compilation error. Let's say I write some ABC letters in the middle of the code. This is wrong syntax in C programming language. You can't do that. So when I try to compile, this is what it looks like when there are errors. So basically it says error, ABC is undeclared. It's just some random letters in the code. So the code didn't compile, it didn't give us the size, and there's some red text, and you can go to problems and it says errors, for errors, ABC is undeclared, and some warnings, statement has no effect ABC. So this is what it looks like when you write mistakes in the code. And also this ABC is underlined with a red color. So now, if I delete it, it builds properly, all the mistakes disappear, and I can check out the size of my program. Next thing that we want to do is we want to, for example, turn on or off LEDs. And we will now do it in a special way using direct access to chips registers. This is what the hackers do. They don't oftentimes write some code, they try to write values into registers directly. So to get more information about this chip, for example, which register or which memory address location does what thing, you go to launcher view here. Then you unscroll to your chip. Then you click on documentation. And then you open datasheet, EFM32 Giant Gecko datasheet. And it opens in your default PDF viewer. And you can also open reference manuals. And you have to open EFM32 Giant Gecko reference manual. This is the correct document. And here you have information about the peripherals of this microcontroller, and also about registers which control the peripherals. And first, I want to show you the clock management unit of ARM processors. Similar ones are in other processors, but ARM has it in a certain way. So basically, in this picture, we can see the path of all our clock sources inside the system. And when you turn on the processor, the only clock that is on is high frequency RCO built-in oscillator. So when you turn on the computer, the processor is clocked by this signal, and it goes to our core, on Cortex core. However, all the other peripherals are switched off, and in order to switch them on, you need to enable the clock signal for that certain peripheral. And to do that, you need to set a bit in a register from 0 to 1 to switch on a clock signal to some peripheral. And under register description, there is a register which is called high frequency core clock enable. Sorry, not core clock enable, but high frequency peripheral clock enable. And with this register, by switching some bits from 0 to 1, you turn on that particular peripheral. For example, if you want to use a timer number 0, you first need to switch it on by writing 1 into the corresponding position of the register. And fun fact, general purpose input output is also off by default, so you need to switch it on. So if we want to turn on an LED in the processor, we first need to switch on the general purpose IO clock signal. Otherwise, it will just not work. So to do that, we need to write in clock management unit register named high frequency peripheral clock enable 0 bit number 13. So how do we do that? First of all, the offset of this register is 0x44. I'll write it in my code. I go back to simplicity IDE. So I clicked here. And then inside the code, I will just write 0x044 for now. This is offset. Or I'll write it as a comment. To write a comment, put 2 forward slashes and write a comment. 0x44 is offset 4. And then I just copy the name of this register. Next, bit 13 turns on general purpose input output peripheral. So we need to turn it on so that we can use inputs and outputs like LEDs and buttons. So bit 13 is Gpio Enable bit. We need to set it high. Okay, and now the beginning of clock management unit control registers can be found either in the beginning of this. No, it's not here. So the beginning of clock management unit settings in memory can be found in memory and bus system layout, flash, wait a minute. Here, so this is this picture shows the memory organization of our processor. So in the beginning of the memory is your code, then it's random access memory, and then is peripheral control. It is like a location in random access memory in certain address, and if you write a certain bit in a certain address, something turns on or off or changes settings. And here we can check out that we need to find the beginning of clock management unit. It's right here. And the beginning of clock management unit is at address 0x400C8000. So I'll write it in the comment. Small clock management unit settings start address is in memory location 0x 400C 8000. 400C 8000. So in order to enable general purpose input output peripheral in the processor, we first need to write 1 into bit 13 of a register which is located in this address plus this offset. So, you can calculate it on the calculator, the absolute address of this clock management unit, high frequency peripheral clock enable 0 register. In Windows calculator, for example, you can open programmer's view. In hex write 400C 8000 plus offset 044 is equal to, obviously, 400C 8044. So I'll write it in the comment. Absolute address of this high frequency peripheral clock enable register is 0x400C 8044. So now we need to tell this C programming language that we want to write bit 13 equal to 1 in this register. So to do that, we need to write it in the following way. Type asterisk, then open bracket, then you write uint32t, uint, it is short for unsigned integer, and 32-bit because ARM processors are 32-bit processors, so their memory is organized in 32 bits. So it will be a pointer to unsigned 32-bit integer, and then you put another asterisk, and then you write 0x400C 8044. Writing this means that basically this beginning of this number basically says this is not a number, this is a memory location. So in C programming language, to say that certain number is a memory location, you need to put this part bracket open unsigned 32-bit integer pointer, and then to write into that memory location, you add asterisk at the beginning. So if you don't understand it right now, it's fine. Just type it down, and we will return to pointers later in other labs. So inside this register, you want to write something that turns bit 13 on. So if we go back to our clock management unit registers, high frequency peripheral clock enable. So basically what we want to write into this register is 1 at bit 13 and zeros at all other bits, because basically we don't want to switch anything else on. We just want to switch on general purpose input output. So inside the calculator, we can clear this number, and then in binary, we can just write 1 and then 0 0 0 0 0 0 0 0 0 0 0 0 0. So we want to write this number in hex, or this in binary, or in decimal, it looks like this, such a number into that register, because this number has 0 at the position that we want to switch on. Let me count one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros in front. So this is 4, 8, 12, 13 zeros in front. So if I write this number into that register, it will turn this bit on. So 0x2000. This turns on GPIO clock signal and enables GPIO. Okay, so now I'll try to build this code, and it compiled without errors. So if you type it correctly, it should compile without errors. So doing this, we switch on the general purpose input output peripheral. Now, what we want to do is we want to, for example, switch on an LED of this development kit. Here are two LEDs, LED 1 and LED 0. And let's say we want to turn on LED 0. And now we need to find out to which pin of the microcontroller this LED is connected. And it's written in this document. So I'll just scroll down, and somewhere in this document, it should say about buttons. Here, push buttons and LEDs. So LED 0 is connected to port E, pin number 2, and LED 1 is connected to port E, pin number 3. So we need to turn on the pin of port E and pin number 2. How do we do that? Again, through registers. So let's check out the data sheet of this processor. Sorry, the reference manual of this processor. And we need to go to general purpose input output peripheral. It's chapter number 32, which is general purpose input output. And you know, in older days, the processors were much simpler. Basically, you could set the pin as input or output and high or low. And in some processors, you could also enable pull-up resistor. So nowadays, the processors are much more complicated. You can set pull up, pull down. You can set it as input, pull up or pull down. You can set it as output, push, pull, output open collector, output wired OR, and so on. So the settings are very many, but we need to use this push-pull option, which means basically you push it high or pull it low. It works both ways. This is the normal, regular input-output situation with output in certain position, either low or high. So we want to use this push-pull mode. And how do we do that? So in register description, we set pin mode using this mode selection register. And since there are so many modes, it's spread across two registers, mode low and mode high. So basically mode high is for pins 8 to 15, and mode low is for pins 0 to 7. So in our case, LED number 0 is on port E, pin number 2. So we will be working with mode L, because pin 2 is in this mode L register. So let's check out. I will copy the register name. The mode register basically tells whether the pin is input, disabled, input with pull, push-pull, wired or wired and limited strength, and so on. So basically, we will want to set it to push-pull, which is mode number 4. So we need to write a 4 across these 4 bits, bit 8 to 11, or the combination 0, 1, 0, 0, basically. So I'll write it here. Decimal 4 is binary 0, 1, 0, 0. So if in this mode for pin number 2 bits I write 0, 1, 0, 0, then everything should work fine. So here I'll write some comments again. So GPIO mode L register offset is 004. Okay. Offset is 0x004. Next, the problem is that we have many ports for this microcontroller. In the datasheet, we can go to pin definitions. We have a, I think, 1995 version. We have port E, port D, port F, and port C, and port B, and so on. So we have very many ports. So this is actually inside the port offset of mode register. So if we go to register map, we would have to find GPIO port E mode. So port E mode low, actually offset is 0x094. So I will correct it here. So it's actually 94. General purpose input output register for port E mode lower 8 pins, offset is 0x094. And the absolute location of this register is we have to add the beginning of GPIO peripheral. So I will again go to memory and bus system. In this picture, I don't know, it's page 17 or something. So general purpose input output is here. General purpose input output starts as address 40006000. So 40006000 is the beginning of general purpose input output. So this location of general purpose input output port E mode L register in the entire processor's memory is these numbers added together. So it's 0x40006094. You know, you just to these zeros you add 94 and you get it. So this is the absolute location. So what I can do is I can write value pointed by unsigned integer pointer 0x40006094 equals 2, and then going back to general purpose input output mode low and using this programmer's calculator in binary mode. So basically what I want to do is write 0, 1, 0, 0 in this part of the register. So I'll write 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0. Oops. So the number looks like this. The first 4s are for this register. The next 4 bits are for this. For third part, it's this. And we want it to be bit number 10 to be 1. So that way we will have mode push-pull, which is number 4, which is basically here. And in hexadecimal, it actually looks beautifully like 400 because in hex, 4 bits turn into one number. It's just happens that way in binary to hex conversion. So 004. So I write 0x400, and writing this line sets port E pin number 2 as output push pull, but by default it's switched off. So to turn it on, I need to set it high, and to do that, the microcontroller has the out register. So it has 16 active bits, and if you write 1 for a corresponding bit, that pin on that port will turn on. So the LED is connected to pin number 2. So in this data out port, I need to write 1 in the second bit position, and then the LED will turn on. So I'm going to try to do that now. So GPIO port XD out, I first need to find out its location. In register map, port E, the out is 0x09C. So 0x09C. The GPIO settings start at the same address as previously. It's the same GPIO. So the absolute address for this is at, and these two numbers added together. So it's basically 0x4000609C. And in this address, if we write a correct value, the LED will turn on. So value pointed by unsigned 32-bit integer pointer 0x4000609C equals 2. And now we need to write 1 in the second bit position, and the rest of the byte, let's leave it at 0. So it will be 1 in binary mode 100, and in hex is just 4, or in decimal it's just 4. So I write 0x4 like this. And now these 3 lines, one of them turns on GPIO, next one turns GPIO port E pin number 2 as output push-pull, and the third line sets this output push-pull in high position. Now I'll compile the code, I will build it, and as you can see, there are no mistakes. The size of the code increased a little bit because there are only 3 lines that we added. Only these lines that are not comments are actually compiled. The comments are automatically removed before compilation. They're just copied to a new file and deleted, and then they're compiled. So the code only increased by a couple of bytes. So now we need to flash it to our development kit to check out whether this code works or doesn't work. Maybe there's a mistake. To do that, you need to open up this GNU on version 7.2.1 debug folder, right-click on this project 2021 ing S37 file, or on the hex file. I'll show you initially with the hex file. Right-click on it, click Flash to Device. This window automatically fills out all the necessary information. It automatically found the development kit and chip name. It automatically selected this hex file, and you basically just click Program, and it will flash into the device. But here's a mistake. And the problem is that you need, in my case, the problem is this. Before you flash to device, and actually you just can leave it that way, you need to switch on the board. For example, in my case, I haven't switched it on, so it doesn't work. So here is a switch on the development kit, and you need to switch it to position to the right. So just slide it to the right position with this advanced energy monitor switched on. So middle position is off. Right position is that you supply it from USB, and the left position would be if you want to supply it from this battery. So you can insert a coin cell battery and you can power the development kit from the battery. But since we're not using a battery, you switch it to the left, so it's supplied by USB power. Okay, so I switch on my development kit. I slide this switch to the left position, and now I'll try once more. Program. Now it flashed. Now it worked. And I look at my development kit. I cannot show you it right now, or maybe I can. I don't think so, but the LED switched on. So on my development kit, this LED number 0, it's switched on and it's now shining. Okay. So how do we switch off the LED? Let's write a simple blinking application. To switch off an LED, you need to write a 0 in this data out register. So mode only initialized the pin as output, but setting low and high is done in this out register. So if you write 0 in this register, the pin will be off. And if you write 1 in this register, the pin will be on. So let's write a simple program. So let's just copy this line. This switches the LED on, and I'll write a comment. And I'll copy this line, and I write 0x0. This switch is LED off. Okay. So writing 4 switches the bit 2 on, and writing 0 switches that bit off. And now to make it blink, we need to put some code between these two things so that, otherwise they would blink really, really fast. For your information, this processor runs at 14 megahertz by default at startup. So when you turn on the processor, it automatically runs at 14 megahertz. Okay. So writing these two lines, the LEDs will blink at approximately frequency of 7 megahertz, or in reality, it would be something like a bit over 1 megahertz, but they would be just switching on and off very fast. So what we need to do is we want to make the processors do something between switching the LEDs on and off. So we will write a function which just wastes some processor time. And we will do it in the following way. To make a new function in your code, you have to write it outside of your main function. For example, here between the hashtag includes and before int main, and you write it like this. For example, this will be delay 1 second function, which doesn't return anything. So we write void delay 1 sec, and it receives no argument. So I'll just write void here. And so if we know that the processor runs at 14 million per second, let's make it count from 0 to 14 million. And then it will take 14 million clock cycles to do that. And we will have a delay of 1 second. So let's try to do that. We will write a very simple loop. Let's create a variable of 32 bits. Just simple counter I, and let's write a loop. for I equals 0, I less than 14,000 million, I plus plus. So basically we just tell, do nothing. So basically we tell the compiler set E equal to 0, then while it's less than 14 million, add 1. And it adds 1, compares, adds 1, compares, adds 1, compares, and so on. And it does it until it counts to 14 million. And when it's done, it exits. And since the processor runs at 14 million instructions per second, it would take, if we don't know anything about assembly, we would think that it will take 14 million clock cycles or 1 second. So I will add this function. After I switch LED on, I will write delay 1 second. And if you're lazy, you can do the following trick. You can write delay. Instead of writing the full function name, you can write the beginning of a function or a variable and click Control plus space, and it automatically completes the function name. So this Simplicity Studio, as many other integrated development environments, has an autocomplete function name or variable name. Unfortunately, Arduino doesn't have it, so you have to type full function name, and if you make a typo, then you have to delete it and so on. So in these advanced development environments, control space and it automatically completes the function name. If there are multiple functions with the same beginning, for example, here, it shows you all options and you can scroll through them and you can double click on one and then it selects it. But in our case, the only function that starts with deal is delay 1 second, and it's like this. So this is our code. I'll make it now to take all the screen so you can see. So we created the new function, which just basically counts from 0 to 14 million. At 14 million, it should take 1 second. So let's build it. It compiled without problems. So we can see 0 problems. And now I will flash it. So I right click on this hex file, flash to device, program, and it flashed. And now you can observe your development kit. And for example, right now, the LED just shines, it doesn't blink. But after some time, it did turn off. And I'm still waiting. And now, after some time, it turns on. And after a while, it turns off. So it blinks, but it doesn't blink at 1 second frequency. It blinks much slower. And the reason for it is that the processor doesn't have one instruction in this loop. It first needs to add 1 to this number, and then it has to compare the number to another number. So it's actually 2 instructions. And the third thing that it does is the branch. So basically, we will check out what the processor does in a debugger. These advanced development environments have a thing called Debug Mode. And what you do is, instead of clicking on hammer, you click on this debug small bug. You click on it, and what happens is your code is compiled and flashed into your processor, and it is paused at the beginning of your code. So the code is not running yet, it is paused. So if you press play here, resume, or press F8 on your keyboard, only then it starts to execute the code. And at any point, you can click pause, and it shows you where inside the code you have paused it. And one really good thing about this environment is that you can check out not the C code, but the actual machine code that the processor executes, because this thing is compiled to smaller instructions. So as I said, you need to increment I by 1, and then you need to compare it. And if comparison fails, you need to add 1 once more. But if it's true, then you exit. So there's a comparison, addition, and branching, 3 different things that the processor needs to do. So instead of 14 additions per second, there's actually more instructions. And you can click on Window, Show View, and Disassembly. And here you can see the actual assembly code that was generated by compiler. So this function, delay 1 second, which comes from lines 4 to line 9. You can see it here in this assembly window. If you're not there, you can also double click on any of the lines and insert breakpoint. Let's try to do that. Let's put a breakpoint at this creation of I by double clicking on the beginning of line 5. So here you can double click and a small ball appears, and it means that there's a breakpoint. Now, if I click resume, the code will execute for some time, but when it reaches this place in code, it will automatically pause. So right now it's doing this loop, it's doing something, then it goes out to turn on or off the LED. So we have to wait until it goes to this place in code. But after some seconds, it should actually get there. So I'll wait for a moment. Maybe it's busy doing something else. Oops, what happened? I'll try once more. So maybe, yeah, the breakpoint is right here. So let's put the breakpoint on line 6, because sometimes when you create a variable, it is the compiler sees that the created variable is only used locally. So the variable is not actually created, but a register inside the CPU core is used to store this variable. So this line number 5 actually never executes. This is why you shouldn't put breakpoints in locations where you create variables, because if the variable is optimized out, or if variable is held in register instead of external memory and you don't initialize it, this line is only in C for C compiler information, but the actual action happens, for example, in this for loop. So you add breakpoint here where something is done with that number. Or maybe you write e equal to 0, then it's an instruction. But if you just create a variable, this is a phantom line, so you don't put breakpoints on those lines. So I put breakpoint here where we enter a loop. So here where e equals to 0, less than 14 million, plus plus. And now I'll run the code. And as you can see, now the code automatically paused on this line, and in the disassembly window, I can check out what exactly happens in this delay 1 second function. And it shows the assembly instructions. And let's see, the assembly instructions aren't really that complicated. But basically, this says that there is subtraction. For example, stack pointer is reduced by some value, then some register is added by a stack pointer. This is just initialization of some variables. But basically, the beginning of the for loop translates to move 0 to R3. So most probably our variable I is actually located in register R3. So I can click on registers view, in general and register R3. I hope that it will be equal to 0. So to walk through instructions in assembly, instead of clicking step into, you click instruction stepping mode first, it's active, and then I click step into. And as you can see, this move means move 0 to register R3. And this S just tells if it's integer, word, or something like that. Next, it is probably compared with some value, and basically move, store, load, add, these usually are fast instructions. So addition of registers is one clock cycle, but branches are slow. They are something like 3 cycles. Loading usually takes 2 cycles, but if it's copying from register to register, it's just 1. So we can approximately count how many lines is one loop. So I'll just count it. So this is the beginning of loop. It's 1 instruction, 2, 3, 4, 5, 6, 7, and then it jumps to the beginning. So instead of one thing, this thing actually does 7 things. So it's at least 7 clock cycles. So instead of counting to 14 million, we need to divide this number by 7. So 14 divided by 7 is 2. So I'll change it to 2 million. Because in each loop, it does actually 7 things. Loads, compares, stores, adds, and so on. And branching takes something like 3 clock cycles. So we can exit the debug mode using this disconnect button, the red disconnected wire, and we're back here. And in this code, I will change it from 14 to 2. And now I'll compile. And then I can press the debug button again. I can remove the breakpoint by double clicking on it and click play. And now the code runs without breakpoints, and I can observe my LED and I see that it blinks faster, but it still doesn't blink with 1 second period. It's actually something like 3 seconds for each blink, because as I said, branching takes 3 extra clock cycles. So we need to reduce this number once more. Let's see, I'll put a breakpoint here. So storing, loading, addition, store from register to register, and load, and the second load and compare are fast instructions, but branch takes 3 clock cycles. So I need to reduce this number by another 1/10 of this, or the original number was 14 million. But each loop takes actually 7 lines, one of which takes 3. So it's actually, I have to divide it by not 7, but by 10, because one of these instructions takes 3 clock cycles. And I get that it only should count to 1400000, and then it will have a period of 1 second probably. So let's just check out. So 1400000, instead of 14 megahertz, it's 1.4 instructions, millions of instructions. So I compile it, I flash this hex file to the memory, and now the LED is blinking with the correct speed of on time is 1 second, and off time is also 1 second. You can also use a chronometer on your phone to check out whether your time is the same. Okay, so now we have created a function which just wastes some some CPU time, such that it's 1 second. And here it turns on the LED, waits 1 second, turns off LED, and waits 1 second. Now, that is basically all for this lab work. So you can just write this code, do everything that I did, compile it, go into debugger, check out the disassembly window, and I'll give you some more information also. So let's say I'm in this debug mode. You can find information about the instructions by Googling their name and adding ARM in front of it. For example, here's a instruction which is called BLS. Well, what does it mean? So I just write ARM BLS, and you can find ARM instruction documentation for your information. This is Cortex M3. So here's ARM Cortex M assembly instructions. You can check them out. And for example, we're interested in this BLS. Okay, branch if lower or same. So it does the comparison and branches. And oftentimes the instruction also has information about how many clock cycles it takes. It's not written here. Let's see, developer ARM com. So branch instruction. And what is the speed of it? Well, it doesn't say, but fine. Anyway, branch means moving around the memory, which clears the pipeline. So if it's a two-stage pipeline, then it needs 3 clock cycles to branch, but fine. So just do this. What I did, try to understand what happens, learn how to use debugger, because oftentimes when you write a code and it doesn't work, it's very good that you can go into the code, put some breakpoints, check out how long time it takes to get from one breakpoint to another. As you saw, you put the breakpoints in the wrong place, it doesn't even execute. So try to do this, and learn how to use the Simplicity Studio debugger. So disconnect, and that's all. And what you have to do, you can try to write a code which turns on one LED but turns off the other LED. But what you need to take into account is if you write D out equal to 0, you clear all of the bits in D out. So if you want to turn one LED on and another off, you need to write the correct 0 in the correct location and the correct 1 in the correct location. And the same goes to mode low. If you want to set the second LED as output, let's see, LED number 1 is on port E pin number 3. So to make it also an output, you would have to write that its mode is output in mode 3 location. So bit 14 needs to be set high. However, I will do it in the wrong way. So this line sets pin number 2 as output and number 1 0 0 0 0 0 0 0 0. Oh, sorry, in binary. So this is 4, this is second 4, second. So if I write this number 4000, so this line sets port E2 output push pull. This second line should set port E3 output push pull. However, if I write this, you can see that by writing port E3 to be output push pull, I am clearing port 2 bits and I set it to disabled state. So this would be an incorrect way to set port E3 as output push pull because it clears all other bits. So the correct way is that you set both of these ports as outputs in the same line at the same time. So you would need to find a number that you write into this register to set bit number 14 high and bit number 10 high. You cannot set one high while clearing all others because then the mode 0 pin is disabled. And the second option is you can write it this way, but you need to write or equal to 0x for 0, 0, 0. In C programming language, this or equal means leave all the bits inside this register as they were originally, but in addition to those which are already set, you also set this one bit high, which is bit number 14. Sorry. So if you write port E2 output push pull this way, then to set port E3 output push pull, you need to write or equal so that the original contents of this register leave port E2 as output as well as set port E3 as output push pull. So to set the bits, you use or equal. You can read about or equal operator on the internet if you don't know C programming language. And yeah, so your task, I leave it here, but your task is to modify this loop in such a way that when one LED is turned on, the other one is turned off. And when the second LED is turned on, the first one is turned off. That is your task. You write the code, you try to debug it, you compile it, and when you have successfully written the code in such a way that one LED turns off, the second turns on, you wait 1 second and the second one turns on and the first one turns off and you wait 1 second, then you copy this code in some text file or in Word document and you upload that code to Ortus as a report of this lab so that I can check out your code. I'll open the document that you upload. I check out the code if it's correct or incorrect. And if it's correct, then you have this lab successfully completed. And if it's incorrect, then you get 0. Or you can try to upload it later once more. So your task is to write in your program this code and then add something here or modify something here such that one LED turns on, but the second turns off. And afterwards, the second turns on and the first turns off. So that's all for this lab.